Okay, here we're looking at some applications of Gauss's law. So what we're going to do now is we're going to actually calculate the electric field using this whole concept of electric flux and how much charge is enclosed. So the first thing that we have to reconcile here is the fact that Gauss's law doesn't work with everything. In fact, it only works with very specific types of problems if we want to reduce the integral to something that's very manageable. Okay? We basically want to avoid having to truly do an integration. So we need to identify the spatial symmetry of the charge distribution. You basically have to see, how is this charge distributed? Is this a problem we can actually use Gauss's law in? And you'll recognize the different types of symmetry that allow us to use Gauss's law very easily. So we'll choose a Gaussian surface with the same symmetry as the charge distribution. So you recognize what your charge looks like. Then you go back and now we're going to wrap a Gaussian surface around this imaginary surface. And we're going to evaluate the integral over this Gaussian surface. Most of the time, evaluating the integral is simply recognizing that the electric field is perpendicular to the surface, and thus E dot dA is just equal to E dA. And again, as long as that electric field can be assumed to be constant, then the integral reduces simply to the electric field times the area. Determine the amount of charge enclosed by the Gaussian surface. This is where we're finding Q. If you remember, Gauss's law says that the electric flux is equal to Q divided by epsilon 0. We evaluate the electric field of the charge distribution using typically the fact that we're going to set EA equal to Q over epsilon 0. And again, we can use these in specific types of problems where the symmetry is spherical, cylindrical, or planar. Again, you'll see why this actually does work, but it does limit us at how many times we can use Gauss's law. Again, we've got to realize what we're getting away from here, or what we're avoiding. We're getting away from doing those crazy integrals that we did in the previous case where we had a wire, we had to integrate using a fairly complicated integral. It was complicated because we had to use Pythagorean's theorem, and it became the square root of the sum of the squares. Just really a nasty integral to evaluate. Here we'll see that we can wrap a cylinder around a wire and we get the same exact result. So let's look at the easiest case. If Gauss's law works, we should be able to get the same result that we got from Coulomb's law. So we're going to go to the point charge, recognize that the field is spherically symmetrical around this charge, and see if we get the exact same thing we got before. So we've got this positive charge right here. We know that the electric field lines radiate in all directions. And we also know by Coulomb's law that the electric field goes by the inverse square of the radius. So as long as a sphere has an equal distance away from this point charge right here, we have our nice Gaussian surface. Now the area of a sphere, of course, the surface area of a sphere, is equal to 4 pi over r squared. And here we're going to see where this 4 pi constant allows us to relate the permittivity of free space to the electrostatic constant. So once again, here's our integral. It's going to become very simple, and that's equal to the charge divided by epsilon 0. So Q represents how much charge is right there. It's nothing to do with the Gaussian surface. This surface right here is really what's on the left-hand side of the equation. So again, let's do our evaluation. We can replace this integral by saying that, okay, the electric field is perpendicular to our surface. It radiates outward. The electric field is going to be constant at that distance, so we can pull that out of the integral right there. And when we take the total integral, we integrate over the entire surface of a sphere. The integral over an entire sphere is really the surface area of the sphere, 4 pi r squared. So this very complex looking form right here for a point charge simply reduces to this. Now, let's take this 4 pi r squared and we're going to move it over to this side of the equation. So we divide both sides by 4 pi r squared, and now our equation looks like this. This is identical to Coulomb's law for an electric field. The main difference is, instead of Ke being out front right here, Ke has been replaced by 1 over 4 pi epsilon 0. So that's the proportionality between those two constants. You can actually check that. Ke is 8.99 times 10 to the 9, whereas epsilon 0 is 8.87 times 10 to the minus 12, roughly. And again, with that factor of 4 pi there, you can see how the two are equivalent. So there we go. I'll go back to this right here. I wish I had written this whole thing out again. But again, this is equal to Keq over r squared. We have, once again, Coulomb's law being equivalent to Gauss's law for a point charge. Okay, now I'll go to the next slide. Looking at the next slide, we're going to look at, instead of a point charge, we're going to replace this with a volume of charge. And in this volume of charge, its volume is 4/3 pi r cubed. We need to do a few things here to set up our problem properly. Again, our Gaussian surface is not going to change. It's still going to be 4 pi r squared. We're going to use that same symmetry. The integral on the left is still going to become E times A, the electric field times the surface area of the sphere, which is 4 pi r squared. But instead of using Q here, we're going to use how much charge we have per unit volume. So Q is going to be replaced by rho. Rho is typically used as mass density, how much mass we have per unit volume. This rho is charge density, how many coulombs we have per cubic meter, per unit volume. So Q becomes V times rho, okay? So again, not too much has changed right here. Again, this volume of a sphere is 4/3 pi r cubed. Capital R is going to represent a constant here. It's not going to be a variable, it's going to be a constant. It's going to be the radius of our charged sphere. Now again, this is not a conducting sphere. This is actually an insulator that has equal amounts of charge distributed throughout its interior. The charge is immovable, but it has a positive charge. Okay, so so far we have this on this side of the equation. Again, this side of the equation is going to become E times A. We can do that because of the symmetry of the whole thing. Again, E comes out of the integral because the electric field is constant. We're just left with the integral of dA, which means we just integrate over the entire surface area. And that again is 4/3 pi r, 4 pi r squared. Okay? So, there it is right there. Electric field times area. Over here, we have volume times rho, the volume of the sphere of charge. And notice, this big R is different from this little r. This little r is how far we move our Gaussian surface above the surface of the charge. The big R, that's fixed. That's however big this little red ball is right there. So as long as we're outside the charge, okay, our equation reduces to this. I'm going to divide both sides by this. That puts pi and pi, or makes pi and pi cancel out right there. 4 and 4 cancel out. And we see that the electric field outside a sphere of charge is equal to the radius cube of the charge times the charge density, okay, divided by 3r squared over epsilon naught. And what this shows us is as we get further and further away from the charge, the electric field drops off by 1 over r squared. It's an inverse square relationship. That's what we expect for the electric field. Okay? So again, we can see Gauss's law has a very nice application right here. It would have been not impossible, but a very difficult integration for this charge right here. Okay? What we would have to have done is create infinitesimal shells, which gradually went from 0 to the radius of the sphere and integrated outward based on those shells. Fortunately, Gauss's law allows us to get away from such a crazy integration. Now, inside the shell, when we're looking at a Gaussian surface, which is actually inside the charged shell, and this is possible. You can do this. It only recognizes what charge it has surrounded. So the charge outside our Gaussian surface really doesn't contribute at all to the electric field. Okay? Now again, small r is the radius of our Gaussian surface. Large r is the radius of our charged sphere. But remember, small r doesn't just represent the Gaussian surface itself. It also represents how much charge is enclosed, or it's related to how much charge is enclosed. And that is the important part. How much of this small volume, or fractional volume of the total, is going to participate here. So again, this is our Gauss's law. Again, all the same simplifications can be made here. Area is 4 pi r squared. But now recognize big R has been replaced with small r. Why? Because we only grab a fraction of the total charge there. So the smaller small r is, compared to big R, the less charge we're actually going to be talking about. So that places r on both sides of the equation. 4 cancels out with 4, pi cancels out with pi. R cubed divided by r squared gives me r. Okay? And we're left with this expression right here. So notice that our electric field is no longer inversely proportional to the radius. The electric field is now proportional to the radius. And what that is going to do is give us a very different profile in terms of how the electric field varies as a function of distance. And in fact, if we combine these two results, inside the sphere and outside the sphere, we see inside the sphere, our electric field goes by this expression right here. Outside the sphere, it goes by 1 over r squared. So here, E is proportional to r. We see a nice straight line. Here, E is inversely proportional to 1 over r squared. Here we see that right there. So the electric field is actually 0 inside this charged sphere. It becomes maximum at the surface of the charge, and then it proceeds to follow the inverse squared law as we get farther and farther away from the charge. So that's sort of an interesting result. Again, even though Gauss's law says that we're integrating, this integral reduces to a really simple form, as is almost always the case for the Gauss's law problems that we do. EA, electric field times the area. Okay? Here we go. This is the electric field of a charged thin spherical shell. Now, again, before this thing was solid, it had charge distributed throughout. Now, if we have a shell, our Gaussian surface, this is a cutaway view, our Gaussian surface is going to enclose no charge, so the electric field inside this thing must be 0. Okay? As soon as we put the Gaussian surface outside, then it reduces to, again, what we had earlier with regard to Coulomb's law for electric field. The electric field is equal to Ke times Q divided by R squared. All right, let's look at a wire. Really go back to the previous chapter where we did some of the integration with the wire, and I can't even remember what the expression looks like. It's really not a fun integral to try to integrate. But in any case, we're going to use Gauss's law to come up with a result here, and we're going to actually see that it is a much better result. Now, first of all, we're doing an idealized situation here. We're taking a wire which stretches out to infinity. So there are some limitations here. If this were a finite length of wire, there'd be some slight deviations, especially toward the end of the wire, as to what the electric field was doing. But if we assume an infinite electric field, which in most cases would give us a great approximation, we surround the wire with a cylinder. The wire itself is cylindrical, so we match it with a cylindrical symmetry. So we do that, and of course, for a cylinder, the two end faces of the cylinder are not important here. And why they're not important? Because the electric field is actually going parallel to the surface. E dot dA, okay, the dot product of a vector parallel to a surface is always 0. So there's no contribution to the ends of the cylinder right here. We're just interested in the outer part of the cylinder, or this part of the cylinder, the curved surface of the cylinder, if you will, and that has an area equal to pi r squared times L. So again, let's look at our Gauss's law for this situation. Gauss's law states that the integral of E dot dA, okay, the surface integral, is equal to Q divided by epsilon naught. Now we're going to make another substitution. We're going to replace Q with the charge per unit length, it's lambda, times the length of the wire, L. And of course, this is just some length that we pick, which is equivalent to the actual length of the cylinder. We're going to see that it cancels out, so it's going to be okay. So once again, the symmetry of our surface matches what we have right here. We can imagine the electric field lines being perpendicular to the wire itself. We go ahead and we do this calculation. Again, replacing our integral with E times A. You're starting to wonder now why we even have that integral right there. Why not always just say E times A? Again, lambda times L divided by epsilon naught. The area of the curved surface of the cylinder is pi r squared times L. L on this side, L on this side. As I predicted, it'd cancel out. And so we move pi r squared over to the other side. And what we notice here is that when we get this, the electric field goes by the charge per unit length divided by pi r squared epsilon naught. Drops off by 1 over r squared. All right? Here's a really interesting result. Let's go back to this for just a second. Again, you do notice right here that it goes by 1 over r squared, but also goes by how much charge we have per unit length. So that's really important to note. Okay, surprising result when we take a look at a non-conducting plate which has charge on it. Again, we're going to talk about charge, but instead of talking about charge, we're going to talk about charge per unit area. We have sigma as representing the number of coulombs per meter squared, times the area itself as representing the charge which is going to be enclosed within a Gaussian surface. Now I'm going to choose a cylinder once again, but now instead of the curved part